degrees Celsius. Okay, let's do another one. Two metal cubes with 3 centimeter edges, one copper and the other aluminum, are arranged as shown in here. Now this is the copper and this is the aluminum. I think it is rather difficult for you to read when it is recorded because I used probably the wrong colors. Copper and aluminum are arranged so that the one end is at 100 degrees Celsius and the other end is at 0 degrees Celsius. What do we need to find? Find the thermal resistance of each cube. Well, the thermal resistance is delta X over Ka. So we need to know the delta X for each cube. Remember, each side is 0.03 meter. That means that is your delta X. And K for copper and K for aluminum we know. Right? Okay, let's put down the result. The area of cross-section for each cube. A cube means length and width and height are all the same. So what is the area of cross-section? Is 0.03 squared, which is 0.0009 meters squared. That is the area of each cube. And K for copper is 401 watt per meter Kelvin. And K for aluminum is 237 watt per meter Kelvin. Refer to the table that I gave you earlier. Now, we need to find the thermal resistance of each cube. Let's find the thermal resistance for copper. R copper is delta X divided by K copper times A. If you notice, for each cube, delta X is 0.03 meter and A is 0.0009 meter squared. Only change will be the value of K. So let's put all these values there. That will be 0.03 divided by 401 times 0.0009. And that will be 0.083 Kelvin per watt. That is the thermal resistance of copper. Similarly, let's find the thermal resistance of aluminum. Our aluminum is delta KL times A. The only difference is, this time, instead of 401 for K copper, we will use 237 for K aluminum. And that will be this number, that is 0.141 Kelvin per watt. So we found the thermal resistance of each cube. What is the thermal resistance of the two cube system? Well, how are they arranged? They are arranged in series. Therefore, the thermal resistance of the system is the sum of the two resistances. Alright, so all the total resistance is resistance of copper plus the resistance of aluminum, and that will be 0.0831 plus 0.141, and that is 0.224, and that is the total thermal resistance. Well, can you now use this to find the thermal current? What is the equation that will help you to find the thermal current? Well, we know delta theta, the temperature difference, equal to I times R. You know the temperature difference, you know the thermal resistance, therefore we can find the thermal current. The thermal current is delta theta divided by R. Delta theta is 100 minus 0. R we just calculated. and therefore I equal to 446.4 watt. Now let me ask you, what does it mean that the thermal current is 446.4 watt? It means if you stand anywhere along the length of copper and aluminum and measure the heat flowing across that section per second, it will be 446.4 joules per second. Now, will the thermal current be different in copper and aluminum? When heat flows from copper to aluminum, will the flow of current be different? What do you think? Well, the flow of current cannot be different. The rate of flow has to be the same. That means the thermal current in copper and the thermal current in aluminum are the same, namely this 446.4 watt. That is very important in doing the next part of our problem. What is the next part that we need to find? We need to find the temperature at the interface. What is the temperature at that interface? Well, for that, I already talked about this. The thermal current in copper is the same as the thermal current in aluminum and is equal to the total thermal current I, which is 446.4 watt. So the thermal current we know, the resistance of copper we know. Is that right? We calculated the resistance of copper in the previous slide. So we know the thermal current in copper. We know the thermal resistance of copper. Can you find the temperature difference between the ends of copper? Yes, we can find the temperature difference delta theta. Our delta theta will be 100 minus theta, because 100 is the temperature on the left end of copper, and if theta is the temperature on the right end, the temperature difference between the ends of copper is 100 minus theta. And now you know that I copper equal to delta theta divided by R copper, and therefore that delta theta will be, you can see 446.4 is 100 minus theta, delta theta, divided by 0.083. We can now solve for theta from there. 100 minus theta equal to 444 multiplied by 0.083. That is 37.1. And therefore theta equal to 62.9 degrees Celsius. That is the temperature at the interface. Okay, let's now talk about the second method of heat transfer. The second method of heat transfer is called convection. Convection. In fact, convection is so much common in nature. Most of the life on earth actually depends on convection currents. How do we get rains? Most of the time during the summer, the air near the earth gets very hot, and you know hot air is less denser. It will rise. Hot air rises and cold air from above will come down. Now the flow of air caused by this phenomenon is called a convection current. Now, you remember my chocolate example. I can ask each student to come here, take a chocolate and go back to the seat. So each student comes, takes a chocolate and goes back to the seat. You can see this is the phenomenon of convection. Convection is a method of heat transfer in which molecules in the warm region of a fluid rise and molecules from the cold region move in. This is because when heat is supplied to an object, it will expand, as we saw in the last part of this lesson. When an object expands, its density decreases. Is that right? A lower density means the object will become buoyant, just like a cork float in water. Air with low density will rise and cold air will sink to come and take its place, causing what is called a convection current. If you put a pot of water on the stove and if you watch it carefully, as the bottom gets hot, the water at the bottom becomes less denser, it will rise, and water from the top will go down. Now next time you put a pot of water on the stove, watch it. You can actually see that convection current. Water from the bottom rising and the water from the top falling, so that the water in the pot will get uniformly heated. So when air gets hot, it becomes less dense and it rises. Cold air will then move in, setting up a convection current. Now let me see if I can demonstrate a very limited convection current for you. Now this is an animation I took from a school science website. Now what this illustrates is you have a candle burning here. When the candle burns, the air immediately surrounding it will rise. And this is a very thin aluminum foil made in the form of a helix. Now what happens is, when hot air rises, that rising air will make that helix spin. You see, the spinning of the helix is an indication that there is air current, and that is convection current. All right, let's start it and take a look at it. There you are. You can actually see, as the candle burns, the hot air rises, and the rising air makes the helix-like aluminum spins. It's a very simple demonstration of convection current. I told you earlier that most of the weather patterns on the surface of the earth are actually caused by convection currents caused by the differential heating on the surface of the earth. Some part of the earth gets hotter faster than the other part. Now, land and sea breeze are good examples of phenomenon caused by differentiated heating and the flow of air that follows. Now, let me explain what a land and sea breeze is. You see, the specific heat of land is much smaller than the specific heat of water. That means during the day when the sun comes up, land will get very hot very fast, whereas the water will take a very long time to warm up. That means air above land will be warm, it will rise, and cold air from the sea will come in to take its place. You see that? Sea breeze. In the evening, the reverse process happens. The land will cool down faster, and the water will take a long time to cool down. The air above water is warm, it rises, and air from land will rush in to take its place, land breeze. So all these phenomena are actually caused by the differentiated heating. Now look at how a room gets uniformly heated by placing a heater at one part of the room. The air immediately surrounding the heater gets very hot, it rises, and cold air will sink, and there will be a good circulation of air created in that room. Now, a mathematical description of convection is a very complex phenomenon. You know,